Hey everyone, welcome to Math 100. We're working on sections 2.1 and 2.2 today. We're going to cover all of section 2.1 and then one topic from 2.2, which is prime factorization. But 2.1 is about understanding fractions. And to understand fractions, it's very helpful to think of some real-world situations and diagrams as well. So we're going to start off with some diagrams here. Fractions represent a part over a whole. Now the whole may be one thing, like a pizza, or it could be a collection of objects, like the whole is all 15 of these. And then the part is the part that we're interested in, such as the shaded part here. So if we're interested in this piece of the pizza, that's one piece, so that goes up on top. And if you look at the pizza, it's cut up into 8 equal pieces, so 8 goes on the bottom, so 8's the whole. Now if you look at this one, here we've got 15 circles, and on yours, I believe they're hexagrams. And then the ones with the X's, we have 6 of those. So this diagram represents the fraction 6 over 15. Your turn number 1. Write fractions for those two shaded diagrams. We have 6 total parts of this one, and the shaded portion are 4 of those, so we've got 4 over 6. And there's no need to reduce the fraction, because if we reduce this, it's going to turn into 2/3, so it doesn't really represent the diagram. So just leave it just like that. All right, for part B, down the bottom here, we got 1, 2, 3, 4, 5, 6, 7 are shaded. And on top, see, we got 7 on the bottom row, 1, 2, 3, 4, 5. That's 12, 13, 14, 15, 16 total. So 7 out of 16 for that diagram. Now fractions also represent division. You can think of them as division. We've got a numerator on top, denominator on the bottom. Make sure you're familiar with those two vocabulary words. So I'll be using those quite a bit. So we take the numerator and divide by the denominator. You can read this as 1 divided by 3. It's the same thing. All right, now we're going to create some sketches representing fractions. So we're going to do the opposite of what we did here. So we have 5 over 9. Now these can be anything. You can make a shape like this if you want, or you can make something real basic. Just a bar with 9 approximately equal. That's 10. They don't have to be perfect. Just make them approximately equal size. If there's 9 blocks, and we're going to highlight 5. 5 nines. Your turn number 2. I got a little creative with this one. There's 8 triangles, and we are going to highlight 3 of them. And they can be anywhere. 3/8. Now the next one, this is the real test to see how well you understand fractions and diagrams. All right, this one's a little different because we've got a numerator that's larger than the denominator. Think about how you can create a pizza diagram to represent the fraction 19/8. All right, so each pizza is going to have 8 pieces. So clearly, if we have 19 pieces of pizza, one pizza just isn't going to cut it. We're going to need more than one. So there's 8, and there's 16, and we'll still need more pieces because we got 19 of them. So there's 3 pizzas, 8 pieces each. all the pieces have to have 8 pieces because we have 8 in the denominator. That's never going to change. All right, now the first one, we're going to need 19 pieces, so we can use all of those. And we'll need all of those. All right, now we got 16, and then we need 19, so we need 3 more. So I'm going to highlight 3 here. And there is 19/8 as a pizza diagram. Now, in real-world situations, it can be really helpful to use a meaningful diagram because it aids in understanding the situation. So, if we're going to create a diagram representing a runner that's 2 miles into a 6-mile race, we might create something like a winding path to represent the winding path of a race. And then since it's a 6-mile race, we'll break this up into 6 pieces, each one representing 1 mile. We'll have to indicate that. And now we're 2 miles into a 6-mile race. So I'm going to draw my little runner here. Oh boy, my artistic skills are. Oh, let me do this way. I don't know, something like that. Okay, then we'll shade 2 miles into the race. And just by looking at the diagram, you get a pretty good idea of what's going on there. If you can tell that that's a runner anyway. And then if we wanted to create a diagram to represent 3/4 of a cup of olive oil, well, one way to do that is by using a measuring cup. We use a measuring cup diagram. So we'll measuring cup here. And then we've got the, I'm not to draw all this, but here we got a line representing 3/4. And then you just fill the thing up. I use green for olive oil. So hopefully your olive oil isn't quite that green. There we go, 3/4 of a cup of olive oil. And, well, it's probably indicating here olive oil. For turn number 3, draw a diagram representing the 2 cars out of a total of 5 were involved in auto accidents. Think about how you could create a meaningful diagram in that situation. All right, so there's 5 cars, and we've got 2 that are all crumpled up. Looks like those 2 have been in accidents. Actually, it kind of looked like they've all been accidents, but maybe these were just minor fender benders, and these were the serious accidents. But anyway, these two have been in accidents 3 out of 5. So 3/5, or yeah, 2/5. 2/5 have been in accidents. All right, now we're going to represent real life situations with fractions. So you're going to read a description and then come up with a fraction. All right, first one's pretty basic. A carpenter uses 7 of the 12 sheets of plywood brought to a construction site. All right, so the part used was 7, and there are 12 total, so 7/12. Your turn, number 4. The Detroit Lions have 53 players on the roster. Of these players, 8 are linebackers. Write a fraction representing the number of linebackers on the Detroit Lions. All right, so the whole is the total number of players, and the part is the number of linebackers, which is 8. All right, now sometimes we're going to have to do some arithmetic in these, so read these very carefully. A conservationist tags 32 deer and 14 elk in a woodland area. Write a fraction representing the part of this group of animals that are elk. All right, so the group of animals is all of the animals, regardless of which type. So that means in order to find the whole for the bottom of the fraction, we need to add together 32 deer and 14 elk. All right, we'll add these two together and get 46. So there's 46 total animals. So that's the whole that would go on the bottom of the fraction. And it's asking for the part of this group of animals that are elk. So there are 14 elk, so that's the part. And total of 46 on the bottom. 14 over 46. Your turn, number 5. The company has 86 female and 73 male employees. Write a fraction representing the part of the employees that are male. All right, so add the two groups together. 90, 15, 159 total employees. So that 159 is going to go on the bottom of the fraction. And the question asks for the part of the employees that are male. There are 73 males, so it's 73 on top, 159 on the bottom. All right, next up, we got a biology class. 13 out of 30 students are full-time students. And in a math class, 15 out of 23 students are full-time. Write one fraction that describes for both classes together the number of full-time students compared with the total number of students. So we're going to need to add together the total number of students between the two classes, and then add together the full-time students. So total students is 30 in the one class and 23 in the other. So 53 total students. All right, now full-time is 13 in biology and 15 in math. Add these together and we get 28. Now we'll create a fraction out of this. Full-time students are the part. Total students of the whole, 28 over 53. Your turn, number 6. When shooting baskets, Ray made 14 out of 22 three-pointers, and Julie made 18 out of 27 three-pointers. Write a fraction that describes for both players together the number of three-pointers made compared with attempts. So I'm going to do the attempts first. Ray attempted 22, and Julie attempted 27. So together, they attempted 49 three-pointers. Made. You got Ray making 14, Truly make an 18, add them together. 32. So our fraction is 32 over 49. So next up is a topic from section 2.2 called prime factorization. And factorization is something that's going to be extremely important for the course. We're not necessarily going to be breaking things into primes, but we are going to be factoring a lot. So this will be very good practice. Now, in order to do a prime factorization, we need to know the difference between a prime and a composite number. So a prime number is a number that's only divisible by 1 in itself. There's no other number that can divide evenly. And by divide evenly, I mean when you divide, you get a whole number. You don't get a decimal. So let's take 5 for example. 5 is a prime number. And if we do 5 divided by 1, we get 5, so that's a whole number. Divided by 2, you get 2.5, not a whole number. And by 3, we get 1.67. Divided by 4, 1.25, so these are all decimals. And then finally we get up to the number itself. 5 divided by 5 gives us 1. So the only whole numbers we get are when we divide by 1 and itself. Everything else gives us a decimal, so these don't divide evenly. So that means 5 is a prime number. If you look at the list of the first prime numbers, you should know as many of these as you can. Definitely up through 13, 17, definitely know those. So 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Alright, so your turn number 7. Determine whether 39 is prime. Alright, so if we can find a single number other than 1 and 39 that divides evenly into 39, then it's not prime. Well, there is one number that divides evenly into 39, and that is 3. That means 39 is not prime. Now, how did I know that 3 divides evenly into 39? Well, I knew it instantly just by looking at it. Why? Because of the divisibility test. And you can do this too. So, we have 3 tests for divisibility by 2, 3, and 5. And these are some really good things to know. So, to be divisible by 2, it has to be an even number. All even numbers end in 0, 2, 4, 6, or 8. So if you see that on the end of a number, you know it's even. So 39, the 9 is not one of those numbers, so that's an odd number. So not divisible by 2. Now, the divisibility test for dividing by 3 is really cool. You take all the digits in the number and add them together. So 9 plus 3 is 12. If 12 is divisible by 3, then the original number is also divisible by 3. Alright, so 12 divided by 3 is 4. That's divisible. That means 39 is also divisible by 3. So that's a great trick to know. You'll end up testing divisible by 3 with a much smaller number by just adding to the digits. So it's a lot easier to figure out whether or not it's divisible by 3. So that's a really great trick. And then for 5, this one's easy. Then if the number ends in 0 or 5, then it's divisible by 5. So those are the 3 that are really important to know. For example, we're going to look at 2475. So is 2475 divisible by 2, 3, or 5? Okay, so it ends in 5. That's not one of our even numbers, so it is not divisible by 2. All right, let's add up the digits. We got 12 here, 16, 18. Sum of the digits is 18. 18 is divisible by 3, therefore 2475 is divisible by 3. 3 works. It ends in 5, so it's divisible by 5. So 2475 is divisible by 3 and 5 and not divisible by 2. Your turn number 8. Determine whether those three numbers are divisible by 2, 3, or 5. So 32. All right, it ends in 2, so that's an even number. So 2 works. 3 plus 2 is 5. 5 is not divisible by 3, so 3 does not work. Does not end in 0 or 5, so that one is only divisible by 2. Part B. It ends in 8, that's an even number, so 2 works. 7 plus 8 is 15. 15 is divisible by 3, so that works. Doesn't end in 0 or 5, so 5 does not work. 165. It ends in 5, so 5 is going to work. Does not end in an even number, so 2 isn't going to work. All right, now we can add up the digits. 6 plus 5 is 11, plus 1 is 12. 12 is divisible by 3, therefore 165 is also divisible by 3. All right, now we are going to do prime factorization. You've probably seen this before. There are a lot of different ways to write this out. A lot of people like to use kind of a tree method, and that's a fine method. So what we're going to do is we're going to write every number we start with as a product of some numbers. Product is multiplication, so we're going to multiply some numbers together to equal the original number. And all those numbers that we're multiplying are going to be prime numbers. So we're going to keep splitting up composite numbers, which are made up of primes multiplied. So a composite might be like the number 6. 6 is 2 times 3. 2 is prime, 3 is prime. Multiply them together, we get a composite number. Think of a composite like a composite material is taking two materials and sticking them together. It's using like flooring and stuff. Well, a composite number is taking two primes and sticking them together with multiplication. All right, so we're going to go through the procedure with some examples. So we're going to write the prime factorization of 14. Okay? So we're going to need to break this up into a prime multiplied by some number. So 14, using our divisibility test, ends in an even number, so that's divisible by 2. So what we can do is write a 2 here, and then 14 divided by 2 is 7, so you get a 7 here. So 2 times 7 is 14. The numbers down here should multiply to equal this thing. Now we need to check to see if these two are prime, and they are. So we're done. So we write 14 as the prime factorization is 2 times 7. Your turn, number 9. Do prime factorization of 6. All right, 6 is 2 times 3. So break it up into 2 and 3, and 6 is 3. All right, next one, 12. So this one will require more than one step. And there's always going to be more than one way to do these, or there usually is. So with 12, we could break it up into 2 times 6 or 3 times 4. In this case, it doesn't matter at all. So I'll do 2 times 6 and break this up into 2 times 3. Now when we write this, notice we have two 2's. So we're going to write this using exponent form. So 2 times 2 times 3 can be written as 2 squared times 3. So there's the final answer in exponent form. Your turn, number 10. So 8 can be broken up into 2 times 4 since it's even. And 4 is 2 times 2, so we have 3 2's here. Now sometimes when you start building these trees out, it can be helpful to circle the primes. That way you don't lose them. The biggest mistake I see students make, other than just dividing wrong, is losing one of the primes as you go as you start making all these tree structures. So keep track of all your primes. As soon as you get one, circle it. And so 8 equals 2 to the third power. Next up, we're going to do 16. Now with these, I like to make tree structures going to be kind of symmetric. You could do 2 times 8, then you have to break up 8 into 4 times 2, and then 4 into 2 times 2. So you're going to get 1, 2 here, and then one that kind of goes off like that. If you want to avoid having a big tail on one of these, try to come up with numbers like that. They're kind of close to each other in value. So 16 can be broken up into 4 times 4, and then each of these can be broken up into 2 times 2 and 2 times 2. So 16 equals 2 to the 4th. Of course, you can do it any way you want. It doesn't matter to me, but this is kind of a little more compact way of doing these. Your turn, number 11, 36. All right, so 36 is 4 times 9. It can also be 2 times 18. And then 4 is 2 times 2, and 9 is 3 times 3. So this is just another example of knowing your times tables makes things so much easier in this course. So make sure you're working on those. All right, so our primes then are a couple of 2's and a couple of 3's. So 36 equals 2 squared times 3 squared. Next up, 84. All right, so here we could do 4 times 21, or you could do, let's see, 84 divided by 2 is 42. So you could do 2 times 42. Either way is fine. 4 breaks up into 2 times 2, and 21 breaks up into 3 times 7. So that makes 84 equal to 2 squared, those are 2 2's, times 3 times 7. Your turn, number 12, 90. So 90 ends in 0, so it's divisible by both 2 and 5. And it is, if you add the digits, it's 9, so it's divisible by 3 as well. So you can pretty much divide by anything. I'm going to do 5 times 18. Actually, no, I want to do something different. I'm going to do 9 times 10. That'll make a nice short tree there. And 9 breaks up into 3 and 3, and 10 breaks up into 2 and 5. So 90 equals 2 times 3 squared times 5. Next up, example 135. Okay, 135, that is 3 times 45, or we could do, I could do that. That's just the first first one that came to mind, so let's work with that. And then 45, that is 9 times 5, and 9 is 3 times 3. So that gives us 3 3s and a 5. So 135 equals 3 to the third times 5. Your turn number 13, 126. So 126, it's divisible by 2 and 3, but not by 5. So to do this one, we could divide by 2, get 63 times 2. I'm going to do 9 times 14. So 9 is 3 times 3, 14 is 2 times 7, and we get 126 equals 2 times 3 squared times 7. Next up, your turn number 14, 225. It ends in 5, so it's clearly divisible by 5. 5, 6, 7, 8, 9. 9 is the sum of the digits, so it's divisible by 3. Ends in 5, so it's not divisible by 2. Alright, so I'm just going to do 5 along with something else. Actually, no, maybe I'll do 25. That'll be easier. Because this is going to be divisible by 25. So we got 4 25s in each 100, so there's 8 in 200, and then 1 left over, so that is 25 times 9. Now 25 breaks up into 5 times 5, and 9 into 3 times 3. That means 225 equals 3 squared times 5 squared. And finally, your turn number 15. We're going to do 350. Now anything that ends in 25, 50, 75, or double zero is divisible by 25. So that is 25 times 14. All right, we got 4 25s in each 100. There are 3 hundreds, so that's 12. And then 2 more in 50, 14. All right, so we got 5, 5, 2 and 7, so that makes 350 equal to 2 times 5 squared times 7. So factorization is something we're going to be doing quite a bit when working with fractions. We're going to need it to do things like simplify fractions, add or subtract fractions. So make sure you get this skill down. Have a great day.